Hi, welcome to the final part of this trilogy, and yes, I didn't know it was going to be a trilogy on these Infineon FET transistors. So if you've seen the other videos, I struggled getting a particular type of Infineon transistor to turn off, whether it was in the Peavey amplifier or on this bench test with a power supply. So that's one Infineon. I thought, right, today I thought I'd test another, and I had the same trouble with an Infineon part. So just to put things right, these are like international rectifiers, and I don't know if there's a Fairchild semiconductor. These are 5 other FETs that all turned off when I put my power supply down to 0 volts. Pick this other Infineon, that didn't turn off, and then this one didn't turn off. So I'm looking at various circuit drawings, and they've all got gate resistors. So trying to get to the bottom of that Infineon issue, the irony is I found an application note by Infineon. It's advised for gate resistor for power devices. So if I scroll down, right, so here's a gate driver, not sure what sort, and the obvious reasons for using a resistor are to limit the gate current from your device. But if you look at some of the gate resistors in many applications, whether it's amplifiers, switch mode power supplies, they're all sort of 6 ohm, 10 ohm, 47 ohm, maybe they start going up to 100 ohm. So when you're talking to 6 ohm and all that sort of stuff, you're not going to limit much current with a 6 ohm resistor. But, so they talk about charging the gate capacitor through a resistor, so that makes negligible difference for charging that capacitor, except with reference to the timing. The slower you charge it, the slower that's going to turn on. So if this is like a dual rail switch mode power supply, if this is slow to turn off when the negative is turning on, you're going to have shoot through. You're going to get current flowing through this one and then through the other FET. I actually experienced that a year ago. One FET was slow to turn off, and it was actually the Miller effect, and I think I spoke about it in one of the videos I did. But this turning on and off can influence the other FET, and it actually gets complicated. They talk about parasitic capacitance between the gate and the drain, and the gate and the source in this example as a transistor, but you also get parasitic inductance, and it's between the legs and the case of all the legs, that sort of stuff. So parasitic inductance and parasitic capacitance, and that's where the problem lies. So we charge the capacitor in the Mosfet up through a resistor and discharge it through a resistor, and that greatly affects the timing. So I scrolled through loads of forums on Google. So some say this resistor is just to limit the current from your device. That's partly true, but as I've discovered with these Infineon FETs, that dampens down the effective tank circuit you've got with parasitic capacitance and inductance in your leads or traces, and they give you rough ideas of what value these should be, but that value dampens down ringing from your power supply and the circuit and the PCB traces, etc, 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 all caused by parasitic inductance and capacitance. So with reference to that Peavey amplifier, I took out an unknown part with an unknown gate capacitance, stuck in an Infineon, which actually got quite a high gate capacitance, something in the region of 5,000 nanofarads. See if I can find it here. I think this is the one, 107 and 20, and look, we've got a input capacitance, 5,340 picofarad, which is actually quite high. But if you scroll down the list for each specific Mosfet, so this one I had the trouble with, it recommends for, like, if you've got a VDD, so 100 volt supply, 10 volts on the gate, 44 amps, they recommend a gate resistor of 1.6 ohms. And you'll see in my test I was using no gate resistor. I did have a gate resistor just for the test, 10k, pulling it down to ground just to discharge that input capacitance on the gate. I think what I've been experiencing on the Peavey amplifier first, then the same issue on the power supply, is this gate loop with parasitics. where the whole system acts like a tank circuit. You turn this system off, the capacitors discharge into the inductance in the leads or traces, and it turns it back on again, and then that charges up the capacitors, then the voltage falls, then the capacitors discharge, and you get a ringing. And because of the capacitance to the supply, which I wasn't turning off, it's constantly ringing and never stops, so never turns off. So first and foremost, have a look at the data sheet. Yeah, I've been caught out with these Infineons. Have a look at the data sheet, and I wouldn't say never put a resistor in, because that's not true. I would always put a resistor in line with the gate, whether it's 4.7 ohm, 6 ohm, 10 ohm, 47 ohm. And in some applications, specifically the Mackie amplifiers actually, you see a 47 ohm, this is just a big resistor I use for an example, 47 ohm to charge the gate, and a diode, reverse biased, that will discharge the gate, but this will dampen out this effect. It's a 47 ohm and a diode. Right, so just to remind you, so 1, 2, 3, 4, 5 non-Infineon FET transistors, none of them had issues turning on and off with the power supply. 2 Infineon transistors that would not switch off. And I've turned everything off to let everything cool down. I've put a 2.2 ohm resistor, because I haven't got a 1.6, 2.2 ohm resistor in line with the gate. Forget the 10k bringing it down to ground, it makes no difference in this scenario. But obviously if it was in a circuit, yes, it'd be prudent to put a 10k down to source. So I've turned it off because when this warms up, the effect of this resistor changes. So this is cold. Right, this is the voltage on the gate. Turn my power supply on. Now I've swapped the rails because this side clicks, so I'm using this side for my 13 volts into the bulb, this side for the gate. Hopefully we'll get this fault to appear now everything's cold. As I say, it's intermittent. Let's see if we can get it to play up. So I'll turn up the gate without blocking the view. Right, so you can see we're in a linear region here, and it's Sod's law, it didn't start ringing. Right, 1.78 amps, 13 volts. Let me just knock the gate down to nothing. Sod's law, it worked. So if I now bypass that resistor, take my word for it, this is intermittent. Sometimes I can get it to ring with this resistor. But so if I move this scope lead down here, I've bypassed the resistor, so now I'm putting the supply directly onto the gate. Bearing in mind this is only a 2.2 ohm resistor, so 2.2 ohm isn't going to be dropping any current, essentially. So power supply straight into the gate. Now I'll turn the gate back up. There we are, that's ringing as I'm turning it on, and it's going through that linear region. And then it suddenly switches on. So we've got 8.2 volts. I think the gate's fully on. Yeah. Right, now I'll turn the gate down to nothing. And Sod's law, it's not ringing. Oh yeah, so I didn't turn it all the way up. I've turned it partly on and fully off. And we've got a ringing. And you can see the current 230 milliamps. And all I did was bypass this 2.2 ohm resistor. So if I move that back to here, 2.2 ohms. So we'll see if I turn the gate up slowly, does it ring as it's turning on? It's ringing its touch there, look. But just a small bit. I'll turn it back on. Well, or just there. So we're at 4.3 volts on the gate. That's passing roughly 100 milliamps. And you can see it's ringing slightly. So that's turning on and off, or that's acting like a tank circuit. That's with a 2.2 ohm, and Infineon on that data sheet with 100 volts and 44 amps, they recommend 1.6 ohm. And turn the voltage down, back to nothing, back up, off, on, off. So in this application on the bench, that 2.2 ohm resistor isn't quite enough to dampen out the inductance and capacitance everywhere. Just there we are. So that's ringing there. If I can get it to trigger. So that's ringing at 3.3 megahertz. Obviously these long leads don't help, but don't forget this original Infineon transistor was doing this in the Peavey amplifier. And the Peavey amplifier has got a 6.2, 6.4 ohm. So in that application with this part, that 6.4 ohm wasn't good enough. Needed to be bigger. Well, so I'll move this lead about, see if I can get it to ring. Well, I've taken my scope lead off the gate, and I'll see if I can get it to ring just like this, which it did earlier when it was cold. That's mildly warm now, so. Right, so we've got to watch this current when I turn it down. Right, that's on. It's turned off. On, off, on. Now it's turning on and off all the time. So I'll bypass that resistor again. Take my word for it, this was ringing with that resistor. Wait, I've bypassed that resistor, and you saw it ringing all the way up to it finally switching fully on. I'll turn it off. That's just that the scope lead's not even connected and it's picking up that noise. So let's quickly connect that to there before it gets too hot. And that's what I've been suffering with. So 230 milliamps. Don't forget this is an Infineon part, different to the original, but still Infineon. If I want this, let's see what amplitude we've got. So it's DC coupled, so the 0 is in the middle. So we have got 19.5 volts peak to peak at 2.3 megahertz. So it's turning on and turning off 2.3 million times a second, giving us our continual current. So that's this Infineon part, and it's got to be 50 degrees or more. Well, I'll turn everything off. I'll try the original part and see what that does. Right, I've taken that transistor off. It was actually from Farnell, this one, and look, the Infineon 80R360P. Have a look at the data sheet. Look, 800 volts, 13 amps. I was going to use that for a specific application. So I just obviously have to watch the gate resistor if I use this, compare it to the one that's already in the circuit. So now back to this one, which showed itself to be less than suitable in the Peavey amplifier. So to satisfy all of you that say, oh, you need a gate resistor, here's a 10k, but I did try it previously with a 1k, it made no difference. So 10k from gate to source. There's my 2.2 ohm resistor, which seemed to be fairly steady on this one, but take my word for it, it's intermittent. So scope, 2.2 ohm resistor, power supply, and same setup as before. So now I've got my 10k gate resistor plus a 2.2 ohm in line with the supply for the gate. Turn the power supply on, 13 volts, which if you look at this power supply video, this is actually rock solid. Right, watch, hopefully my arm's not going to be in the way. I'll turn up this gate. So this is what we couldn't see just with using voltage and the current on this power supply. So turn the voltage up slowly. There we are, in the linear region. Look at that, oscillating. 2.3 megs, 16 volts peak to peak. And I've only got 4 going in, so the voltage must be multiplied from the drain, must be. So if I turn it up, right now it's fully turned on, 1.81 amps, or 1.8. This has actually got a lower on resistance than that previous one. Right, so we've got 2.2 ohm resistor in line with that gate. Turn it down, and bugger me, look at that. It's ringing and not turning off. So we've got 170 milliamps, whereas before we had 180, or then the other week I had 230. That's for that 2.2 ohm resistor. So in this scenario, 2.2 ohm resistor isn't enough to dampen the ringing from all these leads and the parasitic capacitance and inductance on this Infineon FET. So I'll up this resistor. Right, I haven't got a 6 ohm to sort of mirror the Peavey. I've got a 5.6 ohm. So there's my power supply to the gate, 10k to ground still, drain on the back. Right, 13 volts still. Turn up the gate. Still ringing, which is good, because it's ringing on the Peavey amp. Right, now turn it off. Oh, it rang for a bit. Oh, there we go. So it was intermittent in this setup on the bench with these longer leads, but so 2 or 3 times it did fully turn off, and then this last time it didn't, and we're drawing 130 milliamps and it's ringing. So depending on the speed, it's turning on and off. Let's try it again. So that's a 5.6 ohm. There we are, it turned off that time. See, we're down here. Try again. That ringing as it turns on, that is totally undesirable, because when we're in the linear region anyway, it's going to be getting hot. This is just going to be making it worse. There we are. So now it's stayed on again, 140 milliamps. So that's with a 5.6 ohm, which is close to that Peavey amplifier, which I think is 6.2, 6.4 ohm. So roughly 6 ohm clearly isn't good enough for that package. Right, so now I've got a 22 ohm. I'll turn the power supply on. So 13 volts. Hopefully my arm's not in the way. It doesn't look like it is. 22 ohm on the gate. So we don't want it to ring when it's turning on or off. Oh, did something there. Just, yeah, look, 4 volts, started to ring a bit. Less than before though, which is good. Right, so we've got 7.3 volts, 1.8 amps. And let's turn it down slowly. And we'll just look there, that's with a 22 ohm. But doing it fairly, fairly quickly. So with that 22 ohm, it's turning off. With 6 ohm or close to 6 ohm, it wasn't. It was 2.2 ohm, it wasn't. And I have got the 10k from the gate to the source. Discharging any gate capacitance. But you can see there, it's not all about gate capacitance. It's about gate capacitance and the parasitic inductance and capacitance between all the leads and all the package and all the traces, all the tracks, everything. And it just so happens this Infineon package was a nice voltage, nice current that I thought I would choose for the Peavey. Yeah, it's the worst for ringing. Worse than this one, for example. But you can see why I got led up the garden path. All these not made by Infineon, none of them ring. None of them. This IR rectifiers, international rectifiers, 4227 or something, that I put that in the end and it was perfect. Let me put one of these on and I'll show you, but let's try and stop this ringing first. We'll go find a 47 ohm or something and test that. Right, so I happen to have this 47 ohm to hand just for demonstration purposes. This is a 4148 diode, so we'll be charging that gate capacitance via 47 ohm resistor, and when we turn the supply off, it will be discharging through this diode, and this in conjunction with that should dampen down any oscillation. Let's put it to the test. Right, so we've still got 13 volts. Turn up the gate. Now I want to see no oscillation here. Is it doing something there? Not bad, considering that's the worst transistor I've got here, the worst for exhibiting oscillation. And I think it's also got the highest capacitance, input capacitance. So that's slowly up and down. We didn't really see much here. Slightly thicker line there, so is something happening? So it's nice and slow, and it doesn't look like it's going to play up. So 22 ohm we had a ringing, so yeah, the next logical step is, well, I suppose 33 and then 47, but I see in a lot of circuits that, yeah, designed by clever engineers, they've got 47 ohm, so that's it. So on, off, on, off. So it's been a long process, but I finally got there. I've heard of this Miller effect before, and as I said, had a problem with the switch mode power supply, and I couldn't, to be honest, I couldn't understand why I had to increase the gate resistance from something like 47 ohm, and I went up to about 150 ohms before the transistor stopped having an effect on this other one, and I was getting shoot through and they were both blowing up. So you have to be wary of different FETs in different circuits and different applications. And obviously with a 47 ohm, we're going to slightly slow down the charging of that gate capacitance, so it's going to turn on slower. But you know, for audio work, switch mode power supplies, for audio applications running at 400 or 500 kilohertz, this isn't going to really be significant. As you get up, as you develop faster circuits, it's a compromise between the on time and the risk of ringing. So this wasn't turning off, but without a resistor, you've also got the risk of the device inadvertently turning on due to stray voltages, capacitors, inductance, that sort of stuff. So I've learned a bit more about gate resistors. Hopefully you have too. The advice you can take away, and I can take away from this, mess with the different FETs, is always use a gate resistor. Always, not to protect the driver, to stop it ringing. Hopefully this has helped. I have learned something. Hopefully you have too. Thank you very much.